Hello everyone, in this lecture, we learn about the bioelectrical activity of cell in excited state, action potential, and local potential. What is action potential? What are local potentials? What conditions are needed for the triggering of action potentials? And what are the characteristics of these two potentials? With this question in mind, let's learn about this section. In resting state, the cell membrane is positive outside and negative inside. When the cell is stimulated, it will quickly change from external positive internal negative to external negative internal positive. The action potential. As the nerve cell is stimulated, a rapid change of membrane potential occurs, which begins with a sudden change from the normal resting negative positive potential to the positive membrane potential, and then ends with an almost equally rapid change back again to the resting potential and is so-called action potential. Threshold intensity. It is the smallest intensity of stimulation that can increase the membrane potential, reaching to the varying level to trigger the generation of action potential in the cell. After understanding the conception of action potential, what are the characteristics of action potential? All or none law of action potential. The stimulus of threshold or supra-threshold intensity applied to the single nerve fiber always produces an action potential of constant amplitude, and the amplitude remains constant along the propagation path. Key point of the law. When threshold intensity is reached, a full-fledged action potential is produced in one cell, and any supra-threshold intensity produces no increase of its amplitude. Once the action potential has been elicited at any point of the membrane, it can propagate to entire membrane of the cell without any diminishment of its amplitude and shape. Mechanisms of action potential. Depolarization. The membrane potential becoming less negative and reach to a varying level, activating the voltage-gated sodium ion channel. Tremendous numbers of sodium ion following to the interior of the cell down the concentration gradient. The membrane potential rising quickly in a positive direction, and it becomes somewhat positive. Active potential and its original. Active potential can be explained by the concepts already developed for describing the original of resting membrane. We have seen that the magnitude of these membrane potentials depend upon the concentration gradient of and membrane permeability to different ions, particularly sodium and potassium ion. This is true for the action potential as well. The action potential is initiated by the transient change in membrane ion permeability, which allows sodium and potassium ions to move down their concentration gradient. The changes in membrane potential occur because of change in the permeability of the cell membrane to ions. We have known that some channels in the membrane are gated, that is, opened or closed by mechanical, electrical, and chemical stimuli. When a cell receives a chemical signal from a neighboring cell, for instance, some channels will open, allowing greater ionic current across the membrane. The greater movement of ions down their concentration gradient alter the membrane potential so that it is either depolarized or hypolarized relative in the resting state. Ionic basis of the action potential. In the resting state, the membrane is predominantly permeable to potassium ions. Very few sodium ion channels are open, and the resting potential is therefore close to the potassium equilibrium potential. The action potential begins with depolarization of the membrane in response to the stimulus. This initial depolarization opens voltage-gated sodium channel, which increases the membrane permeability to sodium ions several hundredfold. This allows more sodium ions to move into the cell, and the cell becomes more and more depolarized until a threshold is reached and trigger the action potential. The membrane potential at which an action potential is initiated is called the threshold potential. After the threshold potential is reached, more voltage-gated sodium channel open. The membrane potential overshoots, becoming positive on the inside and negative on the outside of the membrane. In this phase, the membrane potential approaches but does not quite reach the sodium equilibrium potential. At the peak of the action potential, sodium permeability abruptly decreases and voltage-gated potassium channels open. The membrane potential begins to repolarize rapidly to its resting level. Closure of the sodium ions channels alone would restore the membrane potential to its resting level, since potassium flux out would then exceed the sodium flux in. However, the process is speeded up by the simultaneous increase in potassium permeability. Potassium diffusion out of the cell becomes much greater than the sodium diffusion in, rapidly returning the membrane potential to its resting level. In fact, after sodium channels have closed, some of the voltage-gated potassium channels are still open, and in nerve cells, there is generally a hyperpolarization and a membrane potential beyond the resting level called the outer hypolarization. Once the voltage-gated potassium channel closes, the resting membrane potential is restored. One might think that the large amount of ions across the membrane are required to produce such large change in membrane potential. Actually, the number of ions that cross the membrane during an action potential is extremely small compared to the total number of ions in the cell, producing only infinitesimal changes in the intracellular ion concentrations. If this tiny number of additional ions cross the membrane with each action potential will not eventually move back across the membrane, the concentration gradient of sodium and potassium would gradually disappear, and action potentials could no longer be generated. As might be expected, cellular accumulation of sodium and a loss of potassium are prevented by the continuous action of the membrane sodium ion potassium ion ATPase pump. What is achieved by letting sodium move into the neuron and then pump it back out? Sodium movement down its electrochemical gradient into the cell generates the electrical signal necessary for communication between the parts of the cell. Pumping sodium back out maintains concentration gradient so that in response to a new stimulus, sodium will again enter the cell and create another signal. That's all for today.